is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hi, I'm Lee Bortons, and it's Wednesday, March 12th, 2025. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss lessons each week from our math curriculum for families with students enrolled in a classical conversations community. And I wish that I could just list all the names of you that have been faithful the entire year, because you definitely host as much as we do. And we appreciate the time that we've spent with you. And we're finishing strong with these last couple of weeks. So Kirsty, what do you have for us today?
So today we have lesson 27, complex numbers. More than complex numbers, it is our ND lesson. So we're excited about that. So of course, every week we like to start by looking at our math map and seeing where we are. And you'll see here that we are in imagination or end space, where we're talking about complex numbers. And I just want to address that we call this imagination. And a lot of the times we think that imagination means make believe. And while the two ideas are related, they're not the same. That imagination is using your mind to see things that are perhaps beyond the reach of your senses. And so that's why imagination is such a great fit for what we talk about when we're thinking about dimensions, especially dimensions beyond 3D, because we have to look for patterns. We have to use our minds to see things, right, that we can't actually see with our eyes or experience with our other senses. So that's why it's called imagination. And so, of course, we are working through this year using the complex lessons, and we are using a format that should feel familiar to tutors, because this is the format and the flow that Lee has graciously given us all for the community day. And so this is what we're doing here to model that for you. And then, of course, as we continue to say, you can use any of those domains to participate in this conversation, whether you're using the digits, the naturals, the fractions. All of those domains are going to be looking at the same concepts this week, the same ideas about end space and complex numbers. And so we really encourage families to remember that, right, you can be having these common conversations with all of these domains. And it's really exciting because we're less than a month away from seeing several of these lessons go to print. So digits, integers, and fractions will be available in print, along with monomials, beginning April 1st. And I would encourage you to be watching for that to become available, because there is introductory pricing on those. And then beginning on June 1st, we will have additional digital lessons available, continuing the naturals, adding in the decimals, the rationals, and reals. So we're excited that we're going to be filling out our map as we go. This year, we'll be piloting with binomials. And so notice that just gives us just a few domains left to be developing. So we're very excited. So each week, we are looking at a different way that we can be warming up our math brains. And we've been using the same game from Quick Flip Arithmetic each week, so that we can continue to dive in and see how one game can actually be so tailorable to all kinds of different students, and really give us this limitless supply of practice with our students or ourselves. So last week we looked at trinomials. This week we're going to look at, instead of a monomial and a trinomial, two binomials, which is actually a double application of the distributive property. So the cards that I flipped over were the king, 3, 8, and the ace. So you can see there how we would write that in that form. And then reading it, notice it's a little bit different because we have two quantities. So now we have the quantity 13x minus 3 times the quantity 8x plus 1. And you can see below that I've written this, and what I've done is I've written the first distribution. And so, fun little animation. One of the things I was thinking about with cards is that we can actually help our students to use those cards to kinesthetically understand what we're doing when we're distributing. So the first distribution, we're distributing that whole sum over our second sum. So if I was to look at this, right, I'm taking this entire sum, 13x minus 3, and I'm going to distribute that over 8x and over the 1. So if you have a kinesthetic learner, you could actually have them take and say, the K and the 3, right, the king and my 3, I'm going to take those two cards and distribute that, right, over my 8. So that's what happened. But now I still have that whole sum. It's not just a monomial, it's that whole sum, right, that I'm multiplying by 1, distributing it over the 1 also. And now this may look a little bit more familiar because now we have a monomial and a binomial. We just happen to have it twice. For some students, they may be happy to work what I say backwards, right? So they might say, oh, I can take that 8x and I can distribute it going from right to left. Some students may be more confident going from left to right still. So this is a great opportunity to remind them that the commutative law, right, says it doesn't matter how I write my two factors. So I can actually rewrite that as 8x times 13x minus 3 and 1 times 13x minus 3, right? So all I did was move my two factors. And then I distribute again, right? And so now I have to distribute my 8x over both terms and my 1 over both terms. And you can see that that continues on and we end up there with our trinomial. Now, for those of you who grew up thinking about FOIL, that's exactly what FOIL does. All that FOIL does is it says, I'm going to distribute, right? I'm going to multiply my first term. So that's my 13x times my 8x. My outside terms, that's my 13x over my 1. Then my inside terms, my -3 over my 8x, and my last, my -3 over my 1. So all that FOIL does is give us a mnemonic for helping us to keep track of making sure that we're distributing all of our terms. And this is why I say the distributive property is so important for our students to see, because all of those shortcuts, whether it's writing it horizontally or whether it's writing it vertically, or whether it's using some of the Japanese methods where they use lines, or whether it's using boxes, right? All of those different arrangements, right, are arrangements of the distributive property. They're there to help us make sure that each of our terms gets distributed. And so I hope that that's helpful there. Does anybody have any questions?
I have a comment. As you were doing it, it's probably because I was writing the lesson for it today. But once my student is maybe beginning this and they just can read it and write the 13x minus 3, 8x plus 1, I might then say to them, okay, forget the distribution, because a lot of kids are dyslexic still in 8th, 9th, 10th grade. It's a lot of letters. And so something I can do with them orally is say, okay, now let's find our roots. Let's set it equal to 0. So 8x plus 1, x is going to equal -1/8. 13x minus 3, x is going to equal +3 over 13. So if I did enough of those and pointed with my finger, they would start to see how to find roots of binomials really quickly, because setting them equal to 0 makes things like easier. So you can do that without writing something down if you have an auditory processor who struggles with, do you see why we all make careless errors? It's almost impossible not to make a careless error in this problem.
Yeah, I love that, the importance of speaking things out with especially auditory learners. But even with our visual learners, when we hear it and see it, it's a great reminder. And just as Lee pointed out, right, so one of the reasons why it's so important for us to practice multiplying two binomials and seeing the trinomial is that that's going to help our students when they need to factor, right? So we have not emphasized factoring algebraic expressions yet, because that's something that we're going to start to see in binomials, polynomials, and expressions. But that is an essential algebraic skill that we want our students to develop. And the more that they multiply, right, and they're going to be able to divide, right, which is what factoring is. And so it's just like our numeric facts, where we want to help our students practice those multiplication facts, because then they're going to be able to start to divide more easily because they're going to recognize the pattern. It's the same here. That is, we help our students to multiply through binomials like this. They're going to start to see the patterns that are going to help them then to factor out and essentially divide. So even though we're not here yet, I want to really emphasize that for everybody, right? We're not here yet in the math map. Those levels have not been released. But I also want you to see that whatever level student you happen to have at home and be working with at home, these games are going to be so helpful and really so much better than a drill sheet, right? Because I can just continue to get new problems. All right, and so that brings us to looking at our cover this week and taking our time to talk about this. And so I'm going to start our timer. And what do you see in our art or quote or our reflection this week?
Fractals?
Fibonacci. I don't know what that means, but I know the word and what it looks like.
Yeah, it does have that. It is reminiscent of the things that we see, right, with the Fibonacci sequence.
There seems to be. Oh, go ahead.
I was just going to say, at first glance, you see just like a nautilus looking shell, but then you see this sort of optical illusion, or maybe that's not what it is. It's just you use your imagination and you can see that there are millions of these little shells in the picture. Go ahead, Kelly.
Well, I was just saying it looks like there's an infinite number of these spirals, which makes me think of how you, Dr. Gilpin, have said we don't know how many dimensions there are. It could be an infinite number. And so that's where my mind goes when I look at this.
I love the quote down at the bottom right there, and just thinking of it in relation to this this artwork, and just thinking like, as the perspective we have as we're looking at this art is what I imagine the perspective of God to be, as we are standing down there in the midst of this, which if we're like down in the little part of the spiral or wherever we might be, standing in the midst of something complex like this and looking up, and it just seems overwhelming and impossible to us. But I love the part of that quote that says, "Give me, O Lord, the vision to see the path you set before me." God sees that path clearly when he looks from his perspective, but when we're in the trenches of it, we don't. So I just love that thought looking at this.
Yeah, to piggyback on that idea, every time I see this golden spiral now, I think of Stratford Caldecott's book, Beauty for Truth's Sake, and just how many things he is able to illustrate through both irrational and imaginary numbers, and how, Kirsty talked about the whole imaginary space, and just the truth that we see about our creator, and just transcendent things that we can see through these types of mathematical relationships.
Yeah. And Melba said it's reminiscent of something that's fractalish. Ooh, sorry about that. That it's like a fractal. Right? And that's that idea of self-similarity and repeating images.
You know, and Kirsty, when you get to the point where, okay, so even a young child can see this is beautiful. And then if you can go online and show them some of those fractal images of how all the continents, the surface or area or the perimeter of them repeats these fractals. And then they get older and they start being able to do the Fibonacci series in week 4 and 5 as we practice them. To me, these are the kind of things that help us believe that somebody is looking down and out for us.
I remember one of
like
my
how-
students said that this looked like somebody's hair being braided and that it was very intricate. And I was just thinking, I would have never seen that in this picture. But it was a girl, it was in our class, and she was like, yeah, it looks like somebody really intricately braided this person's hair. I was like, wow, that is really cool.
So
I
let's take
like
a
how
minute. Oh,
there's,
go ahead. Sorry, Jill. You go.
I was just gonna say, I like how there's two parts to this spiral, and the one side seems to require more imagination, and that reminds me of a complex number, that it's got the real and the imaginary side.
I was just going to ask you to take a minute and compare this image of the art to our symbol for ND that's up in the top left-hand corner. And why do you think we might have chosen a symbol like that? What does that symbol make you think of? And why might we have chosen that
It makes me
for
think of
ND?
it makes me think of like the amount of we can go in and smaller and smaller and smaller is so far infinite for our eyes, but God knows. And then it's also the same for out and expanding bigger and bigger and bigger. And as the with the human eye, it seems like historically we saw big first, and then we made microscope lenses and saw small. It's the same lens to use differently, but it just kind of just shows the mind blowing creative power of God to me, and it goes both ways, in and out.
Yeah, that idea of an infinite spiral, right, gives us this idea of infinite. But I love that, Tanya, that we can be looking inward and outward when we're looking um, at these ideas. We oftentimes call it the hurricane because that's kind of what it looks like, although it's probably a spiral. The spiral might be a better word for it, but we've called it the hurricane just colloquially amongst us. And I was thinking about that the other day, that um, hurricane, right, is, for all of its destruction and chaos that it brings, is a remarkably organized and structured weather event, right? And so this almost, right, you almost need your imagination to picture the duality of something having organization and structure and yet creating chaos and havoc. And um, And sometimes we may feel like we're in the middle of the hurricane, not quite the eye where it's nice and peaceful, right? But like on that eye wall where like things are just crazy, right? And we don't know what's going on, and we're experiencing the chaos and the turmoil, but yet God knows, right? There's a pattern, and there's, right, that their peace is coming, that the storm is going to pass, that hurricanes don't last forever. Um, right. And so it just made me think that sometimes when my life feels chaotic and uncertain, that it's happening within a certainty of God, right? That He is still sovereign. Just like when we looked at that image of Jesus on the boat in the storm in lesson 25, right? That God controls that.
It makes me
Something,
wonder about what's in the middle. Like, is there a middle? Is there anything there? Is it just God? Like, or is there an external limit, And is He just the inside beginning and the external limit? I don't know, but you can't really put your finger on it.
That's what our imaginations are so good for, right? Because that's not we may not have answers, and we may not be able to measure something or touch it or feel it or taste it or smell it, but we can think these thoughts, right? And imagine. So, right. Any other last thoughts on our cover before we?
So the hurricane, maybe more than the cover, and made me think about this, how at church each Sunday, we in our liturgy say we're going to pray with the angels and the archangels. And just this image that I try to share with the grandchildren, that's kind of like this, that we can't see them, but when your dad's on his knees praying, you can be sure that demons are fighting those angels, and those angels are praying that your dad's prayer will be effective. And the best thing you can do is quietly uplift your father and join him in your prayers. And I try to give them this vision of this chaos that's outside of our calm, peaceful church building, because we're in the eye and all the battles are around us. And so that's what it feels like too in homeschooling, right? That, when you sit down with them at night and you just cuddle and read a book or watch a movie, there's so much peace. But all day long, there's 1,000 events you got to go take care of, and everything seems against you. But it's really not true. The Lord's there supporting all of this. There's no real chaos to him.
Yeah, love all these things that Lee just said. And as we're thinking about that hurricane, that one of the things we're going to really emphasize in this lesson and in ND is looking for patterns, right? So trying to find those patterns that give us our structure and our order and help us to find peace even in the midst of craziness. So as we look at our invention page here, and this is a summary, right? We see here, we've kind of got a summary of our dimensions. And so every time that we hit a new dimension, we see that we're adding to this page. So does this feel familiar specifically as an I² page? Does this feel familiar from other pages that we've looked at this year? If you were not a complex student, right? So let's imagine you're all fraction students. What on this page might look unfamiliar to you?
They're pretty complicated graphics.
Have you
The
seen
letter
those graphics
I.
before? The letter I would be unfamiliar, yes. So here's one place where our complex students might go, oh, I've seen that, where they, right, for our younger students in their first year, they may not have seen the letter I. So that's something that might be unfamiliar. How about for those complex students, have we looked at, we've looked at graphing our complex numbers, but have we looked at defining them in a 2D way, or have they really been defined in a 1D way for the majority of our complex students that have gone through this year?
So when we did the 1D lessons, and then they had to be separated. And then because they are difficult in some of the other places where we do some simple calculations, we don't really go too far with 2D or 3D with them. Of course, you can't in 3D. So this is really the first place where there's some calculations that make them have to think more of it. Like in the earlier weeks, we tried to make it almost like your grammar, where you're just multiplying and seeing the forms and what's 2i plus 2i or 2i times 2i. But now we're trying to help you visualize it and understand what you've been doing.
And we
Yeah,
also
so we,
work, I was going to say early on, we worked with a number line that was vertical and called that imaginary, and then it was separate from the real number line, which we labeled it a number of times.
so we've really defined our imaginary number or our complex numbers in a very arithmetic way. And because when we talk about I, what does I equal?
The square root of -1.
The square root of -1. So we've really defined it in this very arithmetic way. And I think one of the things that I enjoy about this lesson is that it's an opportunity to look at complex numbers in a geometric way, right? And so we're going to take some of these ideas of geometry that we've played with over the years, and we're going to connect that to the arithmetic understanding of complex numbers that we've built through the complex year. Now, if you haven't been in complex and you haven't been working on calculating with complex numbers, it may all feel unfamiliar, right? But here's the cool thing. So imagine in a few years' time that your students who are in complex have actually seen complex numbers for at least a week every year for several years. That's going to be a really nice introduction, so that when they hit the complex year, they're not going to be unfamiliar anymore. So all of you who are trailblazers this year, using complex for the first time, right? Future years have a blessing and a benefit, that this doesn't have to be unfamiliar to them. What are some other things on here that you see and think of as being familiar to you that you may have seen in other cases before? Or what might be different to how you may have seen them before?
Vectors?
Yeah.
I was thinking, we in my community are on week 23, so we just are starting the third dimension. And so just the arrangement is very familiar at this point when we have a new dimension.
Thank you, Kelly, for noticing that, because I was going to point out that weeks 2, 3, 9, 19, 23, and 27, the first week of each of the dimensions, the layout of this page is very, very similar. And so if you were to pull those 5 and just look at them separately, you would get a good overview of the math and the graphics and how they change dimensionally.
So Kelly, when you look at this page in 23, is it mostly using coordinates or is it using vectors?
I think coordinates.
Coordinates. So whoever said there was a lot of vectors, that's important. And that's going to be something that, right? So we notice that our students may not the first year, but hopefully eventually they're going to start to notice, hey, I've seen some of these images before, but now they're doing these images with vectors and not just coordinates. And the reason why that is so important to us is because we're going to see that when we talk about ND, vectors give us a way of talking about all of these different dimensions and identifying the commonalities between them. So again, way back when Lee and I started this journey, Lee, from her engineering background, said, I really want students to be familiar with vectors because it's so important to engineering and to physics. And then as we dived into this idea of looking at math dimensionally, we discovered that vectors are essential, really essential, for being able to talk about all of these different dimensions and what they have in common. So we came at vectors from a different point, but God knew, right? Here's just an example of where God knew what we needed to have in this curriculum when we didn't really understand why. But as we dove into it, we discovered it's because it is central to this whole idea of looking at math dimensionally.
This is another place where the math map will give entry to modern technologies that other K-12 curriculums don't look at, because vectors are crucial in graphic design. And as AI gets to the point where we're making more and more videos on our own, that's going to open up more and more job opportunities. And the idea of vectors are really important when it comes to images.
So we're on our I² page, we were really emphasizing the idea that we were in a new dimension, and that we saw this idea that there's going to be vectors involved in talking about dimensions. On our I³ page, what do you see?
I see cosine and sine and a lot of pluses and square roots and squares and absolute values, and even a circle. But the rest looks pretty unfamiliar except for the words on the left.
Well, let's talk about those words on the left because it's true, right? It's one more page where we go, there's a lot of notation here. So let's look just at that column on the left. And what is that column on the left? What does it say?
Operations.
Operations. So take a quick scan down that column. And is there any word in that column that you have not seen before?
Have we seen conjugate?
Conjugate.
Yeah.
Okay.
We have actually seen conjugate. We saw it in lesson 5 when we started talking about multiplication. So we have actually seen conjugate before, even if you don't remember it.
And in Latin.
And
This is true.
it's also a term in chemistry, so it's everywhere.
I'm glad you pointed this out about this column because yesterday was like that for my class. They were pulling out things like, I know the word addition, I know the word subtraction, and I think they were trying to be smart alecky, but I didn't acknowledge that that's what I was like, oh, good. Okay, so you know some of the terms, you know the vocabulary. I think they were like, oh, I was trying to get her to get riled up that we were being snarky.
So this would be a great opportunity to pull out your math map, right? So go ahead and flip to your math map if you have that at home. I don't have a copy to throw up on the screen. I apologize. I should have thought about that when I was doing this. But take a look, if you would, at your math map and down the left-hand side where it talks about the topics and the lesson titles. Does that correspond to most of what we have on our left-hand column here?
Do you mean, do these titles on the left match the math map left?
Yes.
I see it. I can see it. I see the pattern.
Yeah, right.
Like you
There's
first
no,
deal with like single digit, right? And then you
yep.
when you conjugate, it's almost like you're conjugating a sentence. So you're putting two numbers together in operations. And then after that, you start getting really fancy with it, right? Am I?
Yeah, so if we look, right, if we remind our students, right, go back, where did we start this year? We started with just numbers and we were talking about how do we write the notation of those numbers? Well, how do we add and subtract them? How do we multiply them? How do we divide them? How do we calculate exponents and roots, right? So if we go back to where we started our year, right, we've been talking about these in depth at the beginning of the year. We spent a year on each of these operations, right? We've been using them all year. And now, almost in a capstone way, we're coming back and we're saying, hey, let's take a look at all of these operations again. But now we're going to look at these operations not just on real numbers, not just on imaginary numbers, but we're going to look at these on complex numbers, right? So the rules that we're talking about here for operating on complex numbers, they're the same things that we do on real numbers because remember, all real numbers are complex numbers. So what we're looking at, what we're going to discover here is that if we were only looking at reals, all of these yucky looking notations would simplify very quickly. But because we have now, right, the real and the imaginary component, the two parts, we're going to start looking at different ways that we can express this. So what here might be worth memorizing, right? Because we call this our Memoria and arrangement page.
Well, this is not super like profound or anything, but the pronunciation of Euler's as instead of Euler's, and like where did that come from? Why is it like that? Because if you heard it, you wouldn't think it's the same thing if you were going phonetically. So I feel like that's an important thing, even though it's not super profound, just for identification purposes. Can anybody like fill in the gap for me on why it's said that way?
I'm guessing it's how he said it.
Is it a
Yeah,
German last name? So would it be phonetic according to the language the name came from?
No. Could be. It was like even De Moivre. So like even De Moivre, he's French. So this would be something you could go look up. Euler, where's his background? And once again, as we're so American centric, and this is a good opportunity to say, yeah, it's these people aren't even American names. So, they're not common English names. So look it up. Something else I want to point out with the word Memoria, Kirsty asked what you could memorize, and obviously you can memorize any of this, but really this is why it's called Memoria and not memorize, is because looking at it over and over again begins to build a Memoria that you can, fall back on. So Kirsty, when you were talking about the simplification process, I thought that was a really good first look through with our students, is to say to each of them, okay, B just equals 0. Read each equation to me now. So where it's Z1 equals A plus BI, it would just be Z1 equals A and Z2 equals C, to see that all the complex stuff falls off when you substitute B or D, depending which equation it is. And then it will look more like what you did in the math map. And so the Memoria gives you the fundamentals with whole numbers that begin to have a peg with these complex numbers.
Yeah, Kelly, I can't remember. Lee may be able to better answer your question about, is there a page just like this for real numbers in there? I don't think there is a page exactly like this, but we do summarize the operations in chart 8. And then there are the laws that are associated are summarized. So we do see similar summaries. One thing that we wouldn't necessarily see exactly like this is because we usually just think of our real numbers in their rectangular form, right? We usually just think, 5 is 5, whether it's positive or negative. That's really just a rectangular form. Now, we did take a very brief look at how you could look at that in polar coordinates, because your 5 times, right, you could have your 5 where your theta is 0, or your 5 where your theta is 180. And so there we would see there that we could look at it with those polar coordinates, but we wouldn't really look at it using this polar and exponential notation, because those values are just going to drop out. And so we would be left with like r cosine theta, because our I part's going to drop out because there is no angle, no sine, right? Or sine is 0, so that would drop out. So we're left with just that piece, just like Lee was saying. And then again, with our exponential, that's going to, again, the E would just drop out, and we would just be left with our radius telling us. So it's a little bit different, because all of that piece would drop out, because we usually just think of our numbers in their rectangular form, even though we could think of them through this way. Now, I want to point out that Lee has put together in this page, right, as she was saying, you don't have to memorize this, right? But what this could, the arrangement here can give you a great way to practice, right? You could, here's another quick flip game, right? We could flip over 4 cards to give me Z1 and Z2, and then have essentially a blank of this arrangement where, okay, I'm going to find the conjugate of each number. I'm going to write each number in its polar and exponential form. I'm going to look at the absolute value of each number. So you could use this arrangement and the idea of a quick flip, right, turning some cards to practice to practice all of these operations. And I think as students start to do that, they're going to rely less on using the forms that are here that tell them exactly where to plug in each number, and they're going to start to be able to calculate inherently with their complex numbers. Well, let's go ahead and take a look at the charts. And you're going to see that we keep talking about 2 different ideas this week. And so I want to ask you to take a minute to look at chart 1 on the left and chart 2 on the right, and just in 1 or 2 words, what's the big idea of each chart?
The laws. So the commutative associated identity laws, the laws, no matter
Okay,
what.
good.
Okay.
Are there any complex numbers other than the title? Are there any complex numbers on chart 1?
No.
No, just letters.
And not
Letters?
even Z's or I's.
No, yep, there's no I's, no E's.
Z's. Yeah, no Z's.
Z's, sorry. Yeah, no Z's, no I's.
Or E's.
They're
Hey, they're called
what
Zeds,
are
everyone. Just kidding.
they?
Sorry, that was me from Canada.
Hey, are you putting a tariff on that, Zed?
Yeah, and then page 2 does have the complex numbers. They could.
All right. So page 1, no complex. Page 2, all about complex numbers. What's on page 1 that we don't see on page 2?
Vectors?
Vectors. Right? So I really want to point out that there's, right, because there's 2 big ideas this week. And this happens every time we enter a new dimension, that we have to stop and say, hey, there's this whole idea about a new dimension alongside whatever application that we're taking a look at. So if we look at chart 1, everything is about the nth dimension, and everything is defined in terms of vectors. And if we look at that, right, we're told that they're called n vector spaces. And these are the requirements for something to be an n vector space, right? And it talks about addition and scalar multiplication. It talks about translation and rotation. And then it talks about all, as Yating pointed out, it points all those laws. Is all of that familiar to us, even if we haven't seen it described in vector form before? Yeah. So we've talked about addition, we've talked about closure, we've talked about what scalar multiplication looks like. We've talked about translations and rotations, and we're familiar with all of these laws. And so now what we're doing is we're taking these ideas that we have been playing with over the course of the year, and we've been playing with them in the specific context of real numbers. And now we're going really, really broad all of a sudden, and we're saying these things are true for a vector, and that vector can have as many dimensions to it as we want. So by saying, hey, this thing that was true for 1D, for numbers, guess what? It's true for 2D and 3D and 4D and 5D and 6D. So this is a summary of the patterns that are going to hold in all of our dimensions. So if I had 200D vectors, could I add vector U to vector V? And is that the same as vector V to vector U? Yeah, because the commutative law still holds, right? If I had 3, could I rearrange them and rearrange the order that I group them in? Yeah. If I had a 2000 dimension vector and I added the null vector that's all zeros, do I get the same vector back?
Yes, identity.
Yeah. So it's pretty cool. These ideas that we've been wrestling with throughout the year, we talked about them in the context of real numbers. In this lesson, where we talk about ND, we're not saying, we're saying n can be any number. It was true when n was 1. And we played around with it. We saw it was true when n was 2, right? We still looked at this 2D vectors, and then we looked a little bit at 3D and 4D vectors. and these ideas. And now what we're doing is we're saying, hey, here is the general pattern, that it doesn't matter what size vector I have. These rules are true for all of them. So that's the big idea, right? So there's a lot of words on here that may feel like a stretch, but I want to encourage us all, especially as parents, right? Our kids may not see this yet, but especially as parents, I love the fact that the last couple of lessons of the year are summative, right? They're pulling you to go back and look at all of the things that we've been looking at all year and seeing how they fit into one nice cohesive system, right? So these things that we're doing are going to be true no matter what dimension we're in. Isn't that kind of cool?
Yes.
So then that's chart 1. That's looking at ND, right? Then we turn to chart 2, and we're going to put away these big thoughts about our n dimensions, right? And we're going to say, hey, let's take a look at complex numbers. Now, for our younger students, this is just an introduction to complex numbers, right? They're going to get a lot more practice in playing around with complex numbers, but this is going to introduce them, right, to the basic ideas of complex numbers, the basic ideas of operating on those numbers. And they're going to see that each year, right, as we lead towards this. Like the fact that one of the things that we do here at the top of this chart is we really talk about how we can define a complex number geometrically, as well as arithmetically, because for some of our students that have a geometry bent, that may actually help them to make more sense over what they're doing with these complex numbers. So for our Challenge A students who've been working through complex, this may feel like a very restful time because, hey, these are some ideas that we've been talking about. We've been doing this all year. We've been seeing these things with these numbers, and now we're coming and we're putting it all together. So I just wanted to point out, those are the 2 big ideas this week, and you really see it when you look at those 2 charts, the 2 ideas. Any questions about anything that's on those charts?
I have a question, and we may have talked about this, but the I is like a placeholder. It's not a variable. So like if earlier Lee was using the example of 2i times 2i. You're not going to get 2i squared. That's just straight 4i. Is that right?
Well, 2i times 2i would actually be 4i squared. Yes.
Oh, okay.
Yes. So it is, don't think of it, it's not a variable, right? It is not a variable. It is a number. It is actually the imaginary unit, is probably the best way we can think of to talk about it. So if I had 5, right, what I really mean is that I have 5 units, right? And 1 is my real unit. When I write 5, and I'm talking about the imaginary number, my unit, all right, it's the imaginary unit. So I have 5. We skip writing this, right? Because 5 times 1 is 5, and we're just all familiar with, right? But I think this is where when we've emphasized over and over all these hidden zeros and hidden ones, that's one of the things that gets hidden. And so we think this I is something really special. Well, it's just saying, no, this is just the unit that we're counting when we're on the imaginary axis.
Something that I had to struggle with, and Kirsty finally beat into my head, was that when we do that number line going up, I guess she's going to show it to you. We wrote 1i, 2i, 3i, 4i, 5i, so because it's unfamiliar and you'd see it. If you're going to be strictly parallel across the bottom, I should have written 1 1, 2 1, 3 1, 4 1, 5 1 on my number line. But that just gets really annoying.
Yeah, exactly. So my units here, I have 1, 2, 3, right? And what my unit is 1 here, right? 1, 2, 3. my unit, right? It's the imaginary. My unit is I. And so we write that because it helps us to remember the difference, right?
It's
But
like
just as Lee said, right, if I had done this, it would help us to see that we're talking about the same thing. We're just talking about a unit.
Okay, the other thing the mathematicians didn't do though is they wrote an R there instead of a one, but on the I, they wrote an I. So that's the thing that Kirsty and I have gone back and forth with over and over. I am such a pattern discoverer. And if your pattern is not analogous, I cannot see the math until I really, really struggle. And so that's what puts me in sympathy for you and your children, because sometimes it's not their fault. They don't understand. The notation is not clear. So we'll go back and put into, she's got it in her charts, I've got it in the frames. We'll have a problem or two to try to just say, read this. Don't try to solve it or calculate it, but read it.
I have
I'm
a
drawing.
question about patterns. Oh, sorry, go ahead.
Okay, I'm drawing. Kind of. Correct me, I'm wrong. You know, in essentials, when we do diagramming, we talk about imply you, right? You is not there in the sentence, but it's imaginary, it's implied. Am I crazy to say that I see similarity between that and R and I, the imaginary I?
Yeah, I think that yes, we have so much in our language that is implied, whether it's mathematical or English language or, right, think about Latin, where you would just say, I'm trying to think of a Latin word off the top of my head, right? Like agricola, right? Well, there's no article, there's no a, and, or the, they're just implied, right? And so our verbs, right? If I said amo, there's no pronoun, right? But it's implied. I love. And so that becomes hard when you are translating, right? Because you're like, well, where did the pronoun go? Well, it's built in, right? It's there. You have to pull it out. And it's the same thing here with math when we talk about it being another language, right? That there are these things that are implied. And if nobody says to you, oh, well, that's implied, then you are forever going, I don't see it, right? Because it's hidden from you. And so I think that's a great analogy there.
We have to use our imagination. I have a question. You remember last week how we were talking about those graphs and the axes and how things changed side to side, but they were different up and down, or maybe it was vice versa. I think they went up and down and they were equal, but side to side they were different. Okay. Does this I have anything to do with that, this imaginary number? Is there any relationship with that, or is that just like
No,
a fluke?
and that brings up a really good point. So when we look at this graph, right, these are not variables, right? There is not a real variable and an imaginary variable. There is no equation that links the two together. There is no graph of a line in the complex plane that's built off of using like R and I, right? It doesn't work that way. When I have, like last week, when I have this and I have X and Y, these are two different variables that are both real numbers.
So one's a coordinate plane and one is just like a number line, but with a different kind of number line coming off of it.
Yes. So
Ish. Yeah.
yes. So this is my coordinate plane where I have two axes that are both real. This is the really big idea behind a complex number, is that if I was to plot this number 2 plus 2i, it's a number. It's not a relationship between 2 and 2i, right? It's just a number. So the complex plane is like it's the stretching of the real number line, right? So the real number line, if I took all the real numbers and I was to line them up, I would end up with the real number line. If I took all of the complex numbers and I was to line them up, they would create the complex plane. And so each point in that plane is a single number. All right.
Took me the longest time to figure out why you couldn't have a line in the complex plane, but you could have a vector. Because I was going cursive, but my pencil makes a straight line, whether I put a little hook at the end or just two dots. And so, like, just those concrete things are the best we can do to model a thing that the Lord requires our imagination for. And that also is why, it can be difficult in mathematics if the concrete is not so solid that you can take it anywhere. And this is why for 20 years, it's irritated me when parents say their children are advanced or they want to promote them in math. And I'm like, but do they know zero? But do they know one? Like there's so many little details that we get overlooked because our children can be very good pattern finders and fool us into thinking they understand when really they're quite good at the dialectic, but they're not rhetorical yet.
So Veronica has a question about when would we use imaginary numbers in real life, and we wouldn't, right? They don't measure anything in our real world. And so that is another reason why these belong in this imaginary unit. And that's one of the reasons why it was Rene Descartes who actually gave them the name imaginary, right? Because he's like, it was a derogatory nickname. He's like, this is stupid. They're imaginary. Well, the name stuck. And they don't measure anything in our 3D space, right? When we measure things, we're using real numbers. And so in my everyday life where I interact with math, am I going to, oh, here's an imaginary number? No, as Bab says, memes, right? That's true. But they do allow, I think a lot, especially electrical engineers use a lot of complex numbers. There's a lot of things that happen with complex numbers that that are hidden to us in our world. They allow us to calculate with a single number, right? So I can't calculate on the point 2, but I can calculate on the number 2 plus 2i. And so once you get to this lesson, you'll see the last page has a picture of the Mandelbrot set and some of the related Julia sets. And so there's structures that exist in our world, that exist in mathematics, that we can only see by using complex numbers, right? And so this comes back to our whole question about why are we studying math, right? If I'm studying math because I want it to be practical and useful, then once you can operate a calculator and, compute on some numbers and balance your checkbook, balance your budget, go shopping and shop, right? You're done. You don't need the rest of this. But if we think about why do we continue to study math, there's the one argument, right? It's really good brain training. But the real argument is that math is going to reveal aspects of God that he doesn't reveal in any other way. And so when we look at complex numbers, and again, you look at these incredibly complex structures, right? The Mandelbrot set, there are people who get their PhDs just in the Mandelbrot set. It's such a complex structure that is not man-made. It is entirely God created. And we couldn't see that structure without complex numbers. So God has, right, he's hidden things, right, for us to go and search out, right? And so complex numbers are allowing us to search out these hidden, beautiful things, these hidden truths that God has put out there for us to search after. And, so there's my soapbox, right? That why are we studying this? Because it's going to help us to know God more and reveal truth, beauty, and goodness. And that's why it matters.
Kirsty, that reminds me when you were talking about, it was meant to be a slam, but it turned out to be a whole thing. Almost like Babs's students who said, "Oh, I recognize addition," and instead of her taking the bait, she jumped on it. And I think instead of somebody taking the bait on the imaginary, they jumped on it. and said, actually, let's dig deeper. And I think we can always do that. And it's so cool that we can't stump God. We can't come up with a way and him go, oh, well, you know, I don't really have anything for that. He actually does.
Right. So any questions or testimonies from last week?
Can I ask a question? This is just because I'm like educated in Singapore and in public school. And so I remember in high school, we had to start using our scientific calculator for math. I don't know why. I can't remember why do we have to do that, but we did it. Is there anywhere we're going to pull out a scientific calculator in the course of math in the later domains?
So a scientific so there's three basic, there's probably 1,000 different kinds of calculators, but there's really, when you think about it educationally, there's three different kinds of calculators that people usually talk about. There's your four function calculator, and your four function calculator is your addition, subtraction, multiplication, division, maybe your exponents, and roots. That's your basic calculator that just calculates on our basic operations. The scientific calculator, and most calculators these days are scientific. There's not a lot of four function calculators that exist anymore. When we were younger, the scientific calculators were so important because I don't know, raise your hand if you remember, if you're old enough to remember, like having to use trig tables and log tables in the back of your books, right? So I remember that, right? You had to flip to the back of the book and use those tables to calculate um, the your trig or your logs. Well, a scientific calculator took all of those tables and put them on the calculator, right? So that's kind of our early computers that we held in our hands, were because they had, not only did they have all those tables, but they were able to then calculate in between, right? So all of those tables went into your calculator and it became a scientific calculator. And now we were able to calculate logarithms and sines and cosines and tangents, because that's what the scientific calculator did. Now, I just want to make a note. If you remember your log tables, they were always in base 10. Guess what? Calculators work the same way. Look, when you put your log button, or your natural log, it's a little bit different because that's base E, but your log button on your calculator, it's just using those same tables of base 10. That's why many lessons ago, where we were looking at how do you change the base, that's why we have to know how to change the base, because if you want to be able to use a calculator, you have to be able to put it into your calculator in base 10. Okay, so that was the scientific calculator, was all about is all about using sine, cosine, tangent, logarithms. There are places in the math map where we say, hey, pull out your calculator to calculate the sine or the cosine or the logarithm. There's not a lot in the younger years, because what we tried to do was, as Lee said, repetition builds memoria. And so our goal was to use, right, if you think about um, when we talk about our angles, you saw these angles a lot, right? 30, 60, 90, 45. And then from that, our 120s, our 135s, our 150s, right? That we built, and we used those same angles so that students would see the values of those over and over and over again, and they wouldn't need a calculator because it would be in their memoria. Now, as our students do move into our later challenge years, they're going to be expected to be able to look at some of the intermediate values, but we're still going to come back to using those a lot to really emphasize. Because imagine if all of our students graduate and they all know the sine, cosine, tangent of all of those angles in the coordinate in the unit circle, and they know how the Pythagorean triples and so forth, right? And so the other ones that we use a lot are the like 3, 4, 5 triangles and so forth, the 5, 12, 13s, So we use those triples a lot so that we're still working with integers, but it gives our students some pegs. So they see that over and over again. And as they do that, they're going to build this number sense of, oh, wait a minute, right? I know 345 is 90. So a 346 is going to probably be bigger than 90, where a 343 is going to be less than 90 for that third angle, right? And so they're going to start to see that pattern over time, maybe not in 1 year, but over many years. And they're going to have a number sense. So now when they use their calculator, they're going to know, is that calculator giving me a reasonable answer or not? Because they're going to, right, have an idea of what value to expect. Now, the third kind of calculator that you could use is a graphing calculator. A graphing calculator was great for students because they could use it at their desk. And so if a student wants to use a graphing calculator to check their graphs, that's fine. We are not going to be asking students to do a lot of work on a graphing calculator because we want them to become familiar with those functions. So just like we talked about last week and the week before, right? We're practicing these same functions over and over and over again. We're tracing them, we're looking at how we move them around and transform them so that they have an intuitive understanding of at least the shape of those graphs. And I'm going to be honest with you, nowadays with most students that we're dealing with, and even most students in traditional classrooms have computers. So they're going to be using services more like a Desmos. So I think a Desmos is amazing because you can put in all of your graphs, see it big on the screen, use different colors, and it's a great way, I think, of just sort of playing with graphs and discovering. So where the math map is going to teach your students the very basic foundational building blocks of all graphs, they become familiar with those and they want to say, well, what happens here, right? They can become scientists in terms of, doing experiments. And a website like Desmos is going to let them look at the graph and start with y equals x and then say, well, what happens if y equals 2x? Well, what happens if y equals 1/2 x? What if I do all of these different things, right? And I can start playing and looking at the patterns, creating my own patterns to learn from when it comes to graphing. So yes, we will expect students to use a scientific calculator. No, we won't expect them to be using a graphing calculator, but we would think that our oldest students who want to go a little bit farther and dive a little bit deeper and explore with some of these functions may take advantage of a graphing program like Desmos, which is free, or a calculator if they had one, but I wouldn't go out and buy an expensive graphing calculator because there's better tools and it's not needed to be successful in the math map. So does that answer the calculator question?
Yes, thank you. I think the frame pages about the cosine and tangent just jot a memory. Is that I remember using that in high school, which is many, many moons ago. So I was just wondering.
So I'll
Right,
tell a
let's go
story.
ahead.
Let me tell a brief story, Kirsty. So I had a student who did Saxon with me well, her mom, they just used Saxon and they were good at using it. And she went on to college and she calls me up one day and she said, guess what? I'm in trouble. And I was like, what happened? And she said, I turned in my calculus assignment and my professor failed me. And I said, why'd you fail me? And he said, because you didn't have your graphing tape taped to the problem sets. And she said, what's a graphing tape? And he said, that's how you have to do your problems, is on a graphing tape. And she said, I don't even know what that is. And he said, well, then how'd you do your problems? And she said, I know math. I didn't need to have a graphing tape. So he accused her of lying because he was so used to students not knowing how to do math. So I don't want ever a child to be there.
So let's go ahead and take a look at the tops of our pages, and we're going to be taking a look at our complex coordinates and doing a lot of work of locating these coordinates in either the polar form or the rectangular form, and just really becoming familiar with the complex plane. So notice on the left here, we're studying the conversion of z equals 1 plus 1i to polar form. And so we see a diagram where we have our first quadrant of our coordinate, of our complex plane, where here's my 1 and here's my 1i right here, right? So this is my point 1 plus 1i. And we're walking through here how to convert this to polar form. So we need a radius and we need the angle. So our angle, we're going to use tangent because here's my theta. And so this is my right triangle. Right? And so just like we did in our week 16 lesson where we were looking at the unit circle. So my opposite side has length 1. Right? So I want to point out that even though the coordinate is 1i, the length is 1. Right? It's length, its distance is 1. So it's in the I direction, it's one imaginary unit, but it has length 1. And so my real, right, is also 1. And so when I look at my tangent, that's my opposite over my adjacent, 1 over 1, and that's 45. Then my radius is the square root of 1 squared plus 1 squared because that's my Pythagorean theorem. So I have 1 squared plus 1 squared equals r squared, and then that simplifies to the square root of 2. And so my rectangular form of 1 plus 1i in polar form is my radius times cis theta. And I'm going to talk about that for a moment here. And so that plugging in my values, I get square root of 2 cis 45. Now my polar form, its long name is r times the cosine of theta plus I times the sine of theta. And what we do is we take R, I, and S, and we abbreviate this to R cis theta. So it's got its formal name and its nickname, and we all like the nickname because it's just easier to say and easier to write. On the right-hand side, we're asked to look at the complex point and its conjugate in rectangular form. I'm going to be honest with you, the conjugate is always easiest in rectangular form because if you go back to lesson 5, you're going to see if we had something like 4 plus 3 pi, and we asked you to write the conjugate is 4 minus 3 pi. Right? Notice the only thing that we did was change the sign in between. So if z is a plus bi, z bar, we say z bar, or the conjugate of z is a minus bi. So if z is 1 plus I here, we see that z bar is 1 minus I. And so we have 1 plus I here. Here's 1 minus I. And notice all our conjugates are a reflection across the x-axis. Let's go ahead and look at page 2 together. And notice here we're now looking at rotation. This is a big idea in complex numbers that's true for all numbers, but it's hidden, and that is that multiplication is a rotation. We just can't really see it. We don't see it as easily in 1D as we do in 2D. And so we're going to start with a point 3 plus 0i. Right here is my 3 plus 0i. And I'm going to rotate 90 degrees. And when I rotate that 90 degrees, notice that now I have a 0, right, for my real, and 3i. And I can read this. I can either match from over here, I can read it from my graph, or I could see what's happening here, negative 3 plus 0i when I rotate it another 90 to 180 degrees, and rotating to 270 degrees, I end up with 0 minus 3i. And then if I go again, another 90, I get back to 360 and I get back to where I started. And notice each rotation of 90 is multiplying by I. And we see that here too on the right-hand side, we're looking at this point. We take 0 plus 3i, and when we rotate it 90 degrees, right, it's the same as multiplying by I. And if I distribute, notice I have 0i plus 3i squared. I squared is -1. And so I end up with 0i plus -3, or -3 plus 0i, which is my -3. So you're going to see there's going to be a lot of emphasis on rotation in the complex plane in this lesson. And then I'm going to just remind you to keep practicing your logic catechism in class. And I would continue to challenge your students at home to know what their resources are as we finish up the year. And then the family, the support that we have for everybody. And I just want to point out that we have 3 weeks left of this version of the book club. And then on April 9th, we're going to start looking at the games and activities that are on the back of the booklets. So that will be our summer version. Our summer version of the book club is going to be some games and activities. So I would encourage you to have your boards in front of you so that we can take a look at how we could play those games. And I know that we are way over on time. I put my phone in a different place, so I wasn't watching. I apologize for going so long, but I'm happy to answer any questions if anybody has them.
I don't have a question, but I just had an idea this week that I wanted to share. I know not everyone is a Challenge A tutor, but you're probably a parent of a student in Challenge A or working through the math map. Anyway, my idea this week was we are quickly approaching week 29, where our students need to be hopefully working on capturing ideas of seeing the unseen. And I keep reminding and asking my class how they're doing, and they are not doing it. So we often take a little break in the morning in Challenge A. When it's nice out, we go outside. So I thought this week we'd go out and look together to find some things together and point them out together, of seeing some of those unseen things, just to help them like actually go through the motions of doing it. And even if we can't go outside, you know, even through the church we're meeting in, we can find things in there. So just giving them an opportunity to actually try it once if they haven't taken that step yet, so they don't have to be afraid of it. We can even do that with our kids at home too. So just trying to give ideas to other tutors if needed, if your students are stuck as well.
Thank you so much for sharing that, Leslie.
I have a question. I just want to say thank you for all the support we've been given this past year being Challenge A directors in our communities. I've really appreciated all the support you've given us, and thank you so much for that. I was talking to a foundations mom yesterday about the math map and her implementing it next year in her family. So my question is a little bit different, not totally focused on math map specific questions that way. But she's just wondering what that looks like and how to help implement that as her family, like maybe buying 3 different levels each year as she goes through with her kids, or some logistics that way. And then also maybe some support from me, additional, like how I can help as a director to encourage more math map and encourage our community more to be in together with the math map, or is that some of that information coming over the next few months, or dealing with practicum too? I just want to kind of bring that more to my community and just looking at how to do that.
Hey, Amanda, so I would say because of time, Babs and Shauna have a lot of resources to help answer those questions. Babs, I'm sure, but Shauna said you just heard it, so maybe they can correspond with you afterwards, because that's like a whole hour of conversation.
Okay, thank you. Thank you.
Well, and one thing too is you're getting ready, and probably in your area, your book rep is getting ready to do the Math Map at Home events. So that would be a great place to point some of your families to and kind of coordinate. And because I think the book reps are willing to go and do as many as is needed. And those events are a couple of hours long. So the families have plenty of time to look at the books and ask questions. And so that will be a good time for them to plug in there.
And that's great. If I can give her that answer, I'm like, okay, the book reps are working on that. We can meet with you and go from there. So that's great. That's what I need to know. Thank you so much.
And Amanda, we're also planning that when we start the book club, like the 1 through 30 book club again for the fall, that we're going to, where this year we really focused on the in community, we're going to be talking more about what does this look like at home and bringing in those other levels. So those foundation parents that maybe haven't tuned in to the math map before, we're going to really encourage them, hey, come to our book club because we're going to be looking at answering those questions.
Wonderful.
But keep asking these kinds of questions, gals, because it helps us plan ahead for what we need to create next or support next.
Can you talk about the question that's in the chat about the difference in the instructions? Is it not a real difference? Is it just words?
I think it's
You
just
mean-
words. And I think it feels like it's the next, oh, I don't know, maybe I may have, I think I know what happened. I think I had to pull from the newer version. And so that's probably where that wording change was. But
Okay, thank you.
yeah.
I kept looking at the pages. I'm like, am I on the wrong page? Is it one of
No,
the
I
other
think
pages?
when you said that, because I was like, why? And then I remembered that the version that I had to pull from, because I couldn't find the right version. And so I ended up pulling from the latest version for today for some of our images. And that's probably, I tried to see if there were any differences, and that's probably a difference that I just missed.
Well,
Well,
I
thanks.
need to go.
Thanks, everybody. It's been great having you here this week. And I look forward to talking about proofs with you next week. And then just reminding you to be bringing in some things to share that you might have put in your own, right? You may not have created a lesson 29 booklet, but what would you put in your own lesson 29 booklet? What's something you've learned this year or seen? And then testimonies for our final week for week 30. So I hope you'll all come and be willing to share. Have a great week.
Thank you.